Water is an essential element in life on Earth and plays important role as the primary need for all living things.
According to the Ministry of Public Works and Housing 2024, urban households in Indonesia uses approximately 144 liters of clean water per person per day.
However, due to unorganized industrial and household emission, clean water is polluted. Household, textile, and industrial activities are the main sources of dissolved heavy metal pollution in water, leading to the depletion of clean water sources.
Lead metal contamination usually comes from mixed organics and non-organic waste that is often found in household activities. Not only that, lead metal with higher chromium metal content are also found in wastewater generated by textile activities. In addition, many arsenic emissions are also found from mining activities, mineral smelting, and also industrial activities that cause a lot of residue.
Various methods have been used to identify heavy metal contaminated in the water, but they require large instruments, complex preparation, high cost, and specialist experts.
We are here to introduce the fluorescence properties of nitrogen-carbon quantum dots that can be used to simplify the complexity of heavy metal detection techniques with naked eye observations, rapid interpretation, low cost, and low toxic properties. So, here are the research objectives. First, there is identifying heavy metal content in water based on the fluorescence properties of nitrogen-carbon quantum dots. Second, there is analyzing the comparison between absorption graphs and color luminescence spectra between heavy metals. And third, there is knowing the correlation between the absorption graphs and the resulting fluorescence properties of color spectrum in identifying heavy metals.
This research was conducted at Chemistry Lab of 6 Senior High School Yogyakarta, Basic Physics Lab of Yogyakarta State University, and Material Physics Lab of Gajah Mada University.
So, here's how the formulation and synthesis of nitrogen-carbon quantum dots. Nitrogen-carbon quantum dots were synthesized using urea and citric acid in a 3:2 ratio, dissolved in 10 milliliters of distilled water. The solution was stirred using a magnetic stirrer at room temperature for 30 minutes to ensure homogeneous particle size. The mixture was then subjected to microwave irradiation at 750 watts, medium-high setting, and for 15 minutes for carbonization. The resulting nitrogen-carbon quantum dots were dissolved in 10 milliliters of distilled water, followed by sonication to reorganize particle structure through vibration.
The characterization of nitrogen-carbon quantum dots were analyzed using pulse emission scanning electron microscope with 5000 magnification to observe morphological structure, and using particle size analyzer to determine particle size distribution.
The preparation of heavy metal samples includes lead, chromium, and arsenic. First, 1 drop of nitrogen-carbon quantum dots was titrated into 10 milliliters solution of lead, chromium, and arsenic. Second, each metal was prepared at concentration 1 parts per million, 10 parts per million, 50 parts per million, and 100 parts per million. Third, samples were observed in a black box under UV light to analyze fluorescences, color changes due to interaction between nitrogen-carbon quantum dots and heavy metals.
Characterization of metal samples. UV-Vis spectrophotometer was used to measure absorbance intensity within 200 until 800 nanometers. Photoluminescence spectrophotometer measure light intensity within 200 until 1000 nanometer.
So, the first is the synthesis of nitrogen-carbon quantum dots. The field emission scanning electron microscope images show aggregated nitrogen-carbon quantum dots with some individual particles and some with forming large clusters, which can potentially create composite bonds. The particle size distribution is 61.5% of the volume consists of 73.3 nanometers diameter particles and 18% of the volume consists of 2.39 nanometers particles, and 3.6% of the volume consists of 1.6 nanometer particles. These results confirms the successful synthesis of carbon quantum dots, as most of particles are under 100 nanometers.
Absorbance and fluorescence intensity comparison. Chromium. At low concentration, absorbance is high, but at higher concentration, it drops sharply, indicating aggregation or quenching. Fluorescence intensity increased initially, but strong quenching at high concentration lead to a steep decline.
For lead, a similar trend is observed with high absorptions at a low concentration, but a decline at a higher concentration. Fluorescence initially increases, but moderately decreases at a high concentration. This suggests there's a balance between amplification and quenching.
Arsenic shows a consistent decline in absorbance with increasing concentration. Fluorescence decreases gradually, suggesting a more stable interaction compared to lead and chromium.
Now let's talk about quantum yields and energy gap analysis. For chromium, it displays nonlinear energy gap changes, indicating complex interaction, possibly due to aggregation and restructuring.
Lead shows a more stable energy gap at high concentration, suggesting saturation of interaction effect.
For arsenic, it shows significant shifts in energy gap 2 at medium concentration, suggesting structural changes in the transition process. Now, the calibration curve comparison. Absorbance is higher at low concentration and decreases at high concentration, likely due to ion interaction and aggregation. Fluorescence intensity generally increases at low concentration but decreases at higher concentration.
The Lambert-Witt equation is used to fit absorbance and fluorescence data.
And finally, for the conclusion, nitrogen-carbon quantum dots not only measure absorbance and fluorescence, but also actively change optical properties when interacting with metals. The research confirms that each metal has a unique optical fingerprint, allowing detection using nitrogen-carbon quantum dots.
For future application, heavy metal contamination in water can be detected by adding nitrogen-carbon quantum dots and observing fluorescence under UV light. This will produce a glow-in-the-dark effect with different metal character. This research demonstrates the potential of nitrogen-carbon quantum dots as a sensitive optical sensor for detecting heavy metal like chromium, lead, and arsenic in water.
So, that is all the information we have given to you guys. Thank you for watching and listening, and bye-bye!